So last but not least, guys, we're at the last example. So I just appreciate your hanging in there. And we're almost done. So good job. Okay. It's asking us to consider this integral, which again, you're probably going, okay, I can figure out the area under that in like 2 seconds using an antiderivative. True. And so for something like this, an antiderivative would be the best method to use. But because it's nice and simple, it's a nice polynomial function, it's a good one to practice using Simpsons rule. Okay, so that's why we're using Simpsons rule on this. It's really just to practice and get the procedure down a little bit better. Notice that it wants us to split into 4 intervals, which means we're actually only going to have 2 Simpsons shapes. Just kind of keep that in mind. But 4 intervals altogether because each Simpsons shape gets split in half. Okay, so I'm going to go ahead and sketch this because you know me, I like giving a visual of the curve, blah, blah, blah. When you do these, though, you can just use the formula. You don't really need to sketch the graph, but it's really good practice, and it's good for us to have a good visual. Okay, so I'm going to just kind of going to do that over here. And notice we're going from -1 to 3. So I think what I'll do is just kind of factor this to find the zeros, or the x-intercepts. So I take out an x, I've got x squared minus 2. So one x-intercept will be at 0, and the other 2 will be at plus and minus rad 2, which is less than 2, and between 1 it's about 1.4. Okay, positive and negative. So I have an intercept at 0, an intercept at 1.4, and an intercept at -1.4, which is like over here. And then I'll go ahead and just plug -1 in there, 0, 0, and then 1, 2, and 3. So let's do that right here. So like f of 1 would be 1 minus 2, which is -1. So right there. Let me do f of -1 would be -1 plus 2, which is 1. F of 2 would be 8 minus 4, which is 4. And then f of 3 would be 27 minus 6. Oh, yikes, that's all the way up at 21. So that's like up here somewhere. So it looks like it's going like this, and then it's going way up there. All right, so I'm going to use Simpsons rule to find the area between this curve and the x-axis. So notice I've got this area here. I've got some negative area down here. And then I've got like a ton of area that I don't even have room to draw. That's in between 1 and 3. And it's all positive area. Okay. So it's really hard to even visualize this, the Simpsons rule shape, so maybe we won't draw the shapes, we'll just go ahead and use the formula. But let's just kind of figure out where our intervals would be. So I'm going from 1 to 3, so I'm going from, -1 to 3, so I'm going from here to here. And I'm going to split that into 4 intervals, so that's nice. They can have a width of 1. So it looks like I'm going to have a width of 1 here, 1, 1, and 1. So h for this is going to be 1. Okay, so I'm going to do the Simpsons rule formula to find that the area is approximately 1/3, which is h over 3, times the first y value, which I found actually right here. That's my y sub 0, because that was -1 plugged into this function. And so that was right here. So that was y sub 0. So that's 1. And then I have to do 4 times the second one, which was 0, but that was one of our x-intercepts. So that's also where y is 0. And you can see if I plug 0 in here, I'd have 0 minus 0 is just 0. And then this value of 1 is going to get used twice. 1 for the first shape and 1 for the second shape. So I have 2 times f of 1, which is -1. And then I have 4 times the value of 2 plugged into the curve, which we did right here was 4. And then 1 of this long height here, which was the 21. So basically you plug all that in there, add all of that up, and I get, eventually it all ends up equaling 12 units squared. Okay, so that's the answer we get using Simpsons rule. Now for part B, it wants us to go ahead and find the exact value, you know, just to compare to see how close it was. So maybe I'll just sort of use this bubble over here to do the exact value. So for the exact value, of course, we would use an antiderivative. So I need to go ahead and use an antiderivative and of this function here. And so that would be, let's see, 1/4 x to the 4th, and then minus x squared. Okay, but then I need to evaluate that from -1 to 3 and yada, yada, yada. So I would do 1/4 times 3 to the 4th minus 3 squared minus 1/4 times -1 to the 4th minus -1 squared. So this right here would give me 81 divided by 4 minus 9. I'll figure that out in a second. And then this here would give me 1/4 minus 1, so that'd be -3/4. So if I look here, I have some like terms. So I have 81/4 plus, because there's a double negative, 3/4 minus 9, and that ends up being 84/4. And I am running out of room, so I'm going to go ahead and erase this really quick. Okay, so let's extend this down here. So then that gives me 84/4, which is 21 minus 9. And so that gives me 12. So it turns out the Simpsons rule was exact. So Simpsons rule was able to give me the same answer as an antiderivative, which means in this case there was no error. So this is asking, what is the error? 0. Now, of course, it won't always be that accurate, but because this was a polynomial, which was one of the best behaved functions out there, it's very, very smooth and continuous, Simpsons rule was able to get us the exact answer. Now, I did need to give you 2 formulas because this asking for specifically what that is, the error Simpsons. So let me give you these 2 formulas. One of them is for trapezoid, and it looks like this. So that stands for error trapezoid. And the formula goes like this. It's b minus a over 12 times h squared times mf double prime, where the h is the change in x. That's the delta x. B and A are the upper and lower endpoints. So I can squeeze that in. Those are the endpoints. And then this mf double prime is, so mf double prime is basically the maximum value of your second derivative. In fact, not just that, but the maximum value of the absolute value of your second derivative. So it's like the highest numerical value of the second derivative, whether that was a positive value or a negative value. It's whatever the biggest number value was, and then you just make it positive. So that's trapezoid error. That's how you can figure out your error. Simpsons error, that's what this little absolute value error Simpsons means. That formula is b minus a divided by 180 times h to the 4th, and again that h is delta x, and that b and a, those are the endpoints, times mf4. MF4 is the maximum value of the fourth derivative. The maximum value of the fourth derivative of f. These formulas here can help us figure out how much error we had in our measurement using either the trapezoid rule or the Simpsons rule. So I'm going to show you that in fact we were right. There is no error. The Simpsons rule was exactly the same as the actual answer. There was zero error. And so we're going to use this formula to see that. But since I ran out of room, I'm going to flip the paper over again. So ES, error Simpsons, is, once again, it's B minus A over 180 times h to the fourth times the maximum value of f to the fourth. And again, not just the maximum value, but the maximum absolute value. Okay, so in this example, did I even give this example a number? I did not. I think it's example 3. In example 3, the A was -1 and the B was 3. Those were our upper and lower bounds. And the H was actually 1. So this is going to be 3 minus -1 divided by 180 times 1 to the fourth times the maximum value of the fourth derivative. So I need to find all the derivatives. Well, f of x was x to the third minus 2x. F prime of x would be 3x squared minus 2. F double prime of x would be 6x. And then the third derivative, f triple prime of x would be 6. And then the fourth derivative of x would be 0. So since the fourth derivative of x is 0 all the time, no matter what x is, it's 0 all the time. That would have to be its max. So it has to be the max. So it's 0 all the time. So I basically can plug 0 in here, and I would get 4 over 180 times 1 times 0. Well, we know that 0 times anything is 0. So all of this right here would just equal 0. So this proves that there really was no error at all. There was no difference in the answer using an actual antiderivative or using Simpson's rule. These formulas here will be given to you, but you do need to know how to use them and what they mean, because I have seen them up here on AP tests before, but they are given to you, the formulas. Okay, so that concludes this section, and we will work on the problems in class on Tuesday. We'll have a quiz coming up on 5.3 and 5.4 on Thursday next week, and then our test would be the week following. So please come in and see me if you have questions or anything, things I can clarify. I'd be happy to do so.